Okay, so let's look at what are the units on the rate constants for these different ordered reactions. Well, to figure this out, what are the units on the rate?
Molarities per second.
Yeah, the unit on rate will always be molarity per second. And what's the unit on the concentration of A? Molarity, right? So that's going to be molarity. So this is going to equal the constant times molarity raised to the 0 power. So that goes to 1, right? So for this 0 order, we have the rate constant is equal to something that has units of molarity per second. So the units on K then for the 0 order will be molarity per second, or it's sometimes written as molarity s to the minus 1. When I write the capital M, meaning moles per liter, molarity, by hand, I underline it as an indication that this is a capital M, because my capitals and my small m's look the same. So for the first order reaction, again, the rate has the unit of molarity per second, and we've got our rate constant in there, and the concentration of A has units of molarity, but this time those units stay. So what would the unit on the rate constant have to be? It's a little hard to think about, right? Well, we could just treat these units as variables and rearrange it and solve for K. We do that. So then we'd divide both sides by molarity. We'd end up with K equals molarity per second times 1 over molarity, and the molarities cancel out. And so then we end up with a unit of 1 over seconds, or s to the minus 1. The unit on the rate constant changes because the relationship between the rate and the concentration is different. And then in the second order equation, we again with the rate, molarity per second, it's going to equal the rate and the rate constant, sorry. And now we've got molarity squared. Yeah, it'll be 1 over molarity seconds. Or molarity to the negative 1 times seconds to the negative 1. That seems like a really weird unit, and it is a weird unit. Any questions? So we were talking about a very simple decomposition reaction where we only had one reactant decomposing into products. What if we have something a little more realistic, like this generic equation here? 2 reactants and 2 products. Well, the rate is going to be proportional to the concentration of each reactant raised to some power. So there's a rate constant, the concentration of reactant A raised to a power, just giving it the symbol M, and the concentration of the other reactant B raised to a power N. The overall order for this reaction will be the sum of the exponents. So the order is going to be whatever those exponents are added together, M plus N. Like with the simpler reaction, we cannot predict what the order is by looking at the equation or anything like that. We just have to do an experiment or many experiments and figure out what the rate law is. Okay? So this is a rather simple example, but here's an equation, a chemical equation for a reaction. Here it is the rate law. And it's asking us to give the overall order and the order with respect to each reactant. So in this first reaction, what is the overall order? Yeah, overall, it's second order. Yeah, you got to choose a pen. So overall, second order. Because it's the exponents 1 plus 1. Now here we're showing the ones. Sometimes those ones may not be shown. With respect to hydrogen, what's the order? 1, or first order. And with respect to the iodine, also first order. So that wasn't too bad. For this reaction, what's the overall order? 3. It's third order. As we take the exponents and add them together, 1 plus 2. For hydrogen, this is first order. And for my favorite compound, no! So all caps is yelling, right? What is it? Second order. Okay, any questions? Yeah.
Why is that first order and second order? Is that just how it is? Or?
Excellent question. Why is this first order for H2 and second order for NO?
Yeah.
Because people did experiments and figured out that it was. Yeah, there's nothing hidden that we can, tweak out of that or anything. There's no secret stuff that I'm not telling you. It's just because, always good to ask. Any other questions? Okay, so let's look at a reasonable reaction here. And here we've got the initial rate of reaction measured at several different concentrations of the reactants. And we've got the initial rates tabulated here. And from the data, we're supposed to figure out what the rate law is and what the rate constant is. So we've done this before with the simple decomposition reaction. Do you remember what we did? We looked at what happens when we change the concentration of this. How does that affect the rate? And so the person doing this experiment was doing this with a purpose, and so they didn't change stuff willy-nilly. In the first two examples here, first two trials, they just changed the concentration of the first reactant and they kept the second one the same. So any change in the rate is only due to the change in the concentration of the first one. So how did the concentration of this reactant change from the first trial to the second? It doubled. So we doubled that. And then what happened to the rate? It doubled. Is it exactly double? No. Is it really close? Yeah. If this is actual data, we can't expect perfection. There are errors in measurement. There's uncertainty. When you double 0.0035, you get 0.0070. That differs in the uncertain digit from 0.0069. That's entirely acceptable. So if we double the concentration and the rate doubles, what's the order with respect to CHCl3? First order. A first order reaction is directly proportional to the concentration. So let's just remind ourselves. For zero order, the rate is proportional to the concentration to the zero power. For first order, the rate goes to the concentration to the first power. And for a second order, it's the concentration to the second power. So the rate is directly proportional to the concentration of CHCl3. So we could begin writing the rate law. The rate will equal the rate constant times CH, the concentration of CH Yeah, I almost did that right. Cl3 to the first power. So we need to know what's going on with the second one. Okay, so here we have an example where the concentration of the first one doesn't change between the second and third trial, and what's going on with the concentration of the chlorine. It's doubling, right? So that's times 2. And what's going on with this? Well, that's kind of hard to eyeball, so get out the calculator and try 0.0098. Yeah, divided by 0.60, whatever. 1.42. Well, does that match up with anything we learned about? No. What the heck? This is, remember that slide where it says if the reaction rate isn't, if the order isn't obvious, use this? And it gave that weird, let's go back and look at that. Oop, passed it. There it is. This guy. We can use this guy here to help us figure out what the order is. And this kind of looks confusing, doesn't it? It's really not that hard. You're just taking rate equals a constant times your concentration raised to the n power. Essentially the rate log with respect to that one reactant for one of the trials and dividing it by the same thing for a different trial. So n should remain the same, and so then we can solve for n. So that's what we need to do here. So we're going to look at each of these. So the rate for the first one is 0.0069. And so that equals the rate constant times, I don't need a bracket, the concentration of the one we're interested in. We can ignore these two because they're the same and they would cancel out. We can just say, well, they're lumped into the constant. So the concentration of the reactant of interest there is 0.010, and that's raised to the n power. N is what we're trying to find out here. The rate for the other trial is 0.0098, and that equals the constant times the concentration for that trial raised to the n power. So the k's cancel out, and we can take that 0.0069 divided by 0.0098. The numbers would have been nicer if I'd done it the other way around, but it's okay, it works either way. A word about significant figures. When we're doing stuff like this where we've got logarithms and powers and different things like this, then significant figures become a little trickier to deal with. The pattern in the book is that a lot of things are going to have 3 significant figures. And so I'm not going to nail you on sig figs, but I also don't want you showing me 9 places. That's ridiculous. So just try to be reasonable. Also, don't round off to 1 significant figure because you're throwing information away and it's going to cause mistakes. So here I'm thinking that when I divide these two, it would only have 2 sig figs, but I'm just going to keep some extras just to be safe. So I'm writing that down. And then this simplifies, if you remember from our other little experiment here, simplifies to this fraction raised to the n power. So we can actually do that division, which is 0.5. So this equals 0.5 raised to the n power. Now, this isn't one that I can look at and just say, oh, yeah, it must be 2. No. So then we have to do that trick where we take the base 10 logarithm of each side. So take the base 10 log of the left side, 0.70408, and taking the base 10 logarithm of the other side, the exponent comes out and is multiplied by the log of the 0.5.
Does it have to be base 10?
In my current foggy 6 state, I don't know. That's something I can't think
So
about.
I always, when I have to solve like exponents like this, I always take the natural log of both sides.
Well, she's doing it right now, try with a different log.
Yeah, I think natural log would work also, but because you're just doing the same thing to both sides. But I really can't say. So try it and see. So then what we're ending up with here is that n is equal to the log of 0.70408. And I know some of you guys are really good at math, and like I said, my brain is horribly foggy today. So if I screw this up, please yell at me. Oops. That's not. Yeah, I think so. I was wondering about that as I was writing it. That's not right. So the log of this divided by the log of the other one.
Comes out to 0.51.
Yeah. So then n comes out to be 0.51. Now, orders of reaction are not going to be messy decimals, nor will they be complicated fractions. So 0.51 is close to the fraction 1/2, right? So the order is 1/2. So this is an order of 1/2 with respect to Cl2. So that's the rate law. Any questions? Yeah.
When you were going through and we were looking at doubling each of the rates,
Mm-hmm.
from the first, in the CHCl3, we looked at the first two,
Mm-hmm.
and then the second and third one, those ones stayed the same.
Mm-hmm.
And then we looked at the CL2, the first two were the same. Does that matter at all? Or
It does.
Look at where, the first changes.
No, it matters because, from this one here to here, we're changing both of them. So then we can't tell if the rate change is due all to one of them or all to the other, because if it was zero order with respect to this, then changing that concentration would have no effect.
Okay.
But if we're changing both at the same time, then we can't tell what's going on.
That makes sense.
Yeah. So, with a lot of experiments, when you're trying to figure out what's going on, change one thing at a time. That works when you're doing stuff around the house, too.
So the overall order, just to make sure I'm understanding, would be 1.5 here?
Yeah, the overall order would be 1.5 or 1.5. Yep. Any other questions?
I have one more question.
Sure.
So, how would this, benefit, what would we apply this to if we're looking at someone at the order? How does that apply to, rate?
I believe that will get answered later. The question is basically, why would we even need to know this, right? Why does this matter? Yeah, we'll get there. Any other questions? Okay, so we still have to answer part B, right? So I'm going to erase a bunch of stuff here because I used up so much space. I don't have any space left. Oops. Let me get rid of all of this. Well, how can we figure out what the rate constant is? We have an equation. We need to plug some numbers in, right? We need a rate, and we need a concentration for each of these. We have 4 sets of those. Does it matter which one we choose? No, because the rate constant is a constant. Which one do you want to do? The first one, okay. So doing the first one, we've got our rate is 0.0035 molarity per second. And that is equal to our rate constant times the concentration of CHCl3, 0.010 molar, times the concentration of chlorine, 0.010, raised to the 1/2 power. Oops, I forgot the unit. So the rate constant then so let's just do the math and then worry about the units because those are going to be ugly, aren't they? 0.0035 divided by 0.01 divided by 0.01 raised to the 0.5 power. So K equals 3.5. Does it seem like that's too nice of a number? Yeah, it's like, wait a minute, this is all messy and real, and this 3.5? Well, you could try one of the other ones and see if it comes out the same. And that's what it is. I checked in the back of the book. What happens with the units here? Yeah, so this molarity and this molarity will cancel out, and then we end up with molarity to the 1/2 power on the bottom. So we could write this as molarity to the negative 1/2 seconds to the negative 1. There it is. Any questions? I put the 1/2 because this molarity is raised to the 1/2 power down here.
So what if you would have canceled that molarity? Would it have just been?
Well, I can't cancel this one with that one because this is to the 1/2 power.
Okay. So,
Yeah. Are you getting a clue that there's going to be more algebra in this class than there was in 1A? There's going to be. Okay, just fair warning. Any other questions?